Okay, so good afternoon, everyone. Today we'll be looking at our Diels Alder reaction mechanism. And the mechanism for the Diels Alder reaction is pretty straightforward. What really becomes difficult is when you have to predict products and draw mechanisms for the products that you predict. A lot of the stereochemistry that is given in your question is really important. So we want to start off with our general Diels Alder mechanism. So we're looking at our Diels Alder reaction. And for the mechanism, really we want to look at having two species present in our reaction. We need a diene and we need a dienophile. And with the combination of our diene and our dienophile, we'll generate our cyclic product, right? So depending on the choice of diene and dienophile, we can have a cyclical product that can have multiple bonds in it, but it'll always have at least one double bond, right? It'll always be an alkene. But we can have more than just a double bond present in our final product, depending on the identity of our diene and our dienophile. So what is our diene? So when we think about dienes, we're looking at a system where we have two conjugated double bonds. So we're looking at conjugated pi bond systems. So for dienes, some common dienes that you may see are just a plain diene where we have our double bond, single bond, and then another double bond. Another common diene that you may see, right? We can start adding substituents to our diene, right, and add a methyl group to one of the carbons in our 4-carbon chain. You may also see cyclical dienes, right, where we have our conjugated system of a double bond, single bond, double bond occurring in a ring, right? We can have a 6-membered ring or a 5-membered ring where we see this occurring, right? So that's another example. And then we can have a cyclical species, a 6-membered ring for our diene, right? And then we can have electron density in our ring as well. So those are some common dienes. What about our dienophiles? Right, so now I want to think about dienophiles, and really what we want to think about is having just a pi electron, a pi bond or pi pair of electrons, and some common dienophiles. I'm going to just draw a few of them out. Right, we can have C, triple bond N. Another common dienophile, we can have our bond O. We can have some ester functional groups present, right? We can have that as trans or cis. We'll talk a lot more about stereochemistry in a little bit, right? So we can have some cyclical esters, and then we can also have cyclic anhydritic species. So if we have 5-membered ring with an oxygen, 2 carbonyls, you can put a bond in there. That could be another example of dienophile. Another dienophile that you may see, we have a triple bond. We can put a methoxy group on each side of a carbonyl. That would be another example of a good dienophile, or common dienophile. And then we can also have another dienophile that's completely cyclical, right, where we have complete ring structure. And then we have our carbonyls on opposite ends of our molecule. So those are common dienes and dienophiles that you'll see in your textbook and lecture. And we're characterizing a diene as having that system of conjugated pi bonding, right? And it needs to be like we said, a double bond, single bond, double bond. Those will be our diene species. If we have that motif, that chemical motif present, we can call it a diene. And then dienophiles need electron density that can react with our diene, right? So our dienophiles are diene loving, and they react with our dienes. So if we look at the general mechanism for our Diels Alder reaction, really let's take a generic diene. So let's take this diene there and react it with a simple dienophile. Probably the simplest dienophile that you'll see is just our ethylene, right? So we have 2 carbons, and then obviously you can imagine that there should be, we think about other atoms present on our molecule, we should have hydrogens present on that carbon-carbon double bond, right? Carbons need 4 bonds. So if we were to think about the simplest mechanism that we can come up with, we can take our diene, react it with our very simple dienophile, and then with our electron pushing, we call it a conserved mechanism, where we'll generate a double bond and we'll create a ring, right? So now we have a 6-membered ring, and we've generated a double bond in our molecule. So this would be our Diels Alder mechanism, and it's pretty straightforward in terms of combining our diene, which we see on the left. This is our diene, and then our dienophile. So that's our mechanism. So what makes it more difficult is thinking about the stereochemistry of our molecule. So we talked about the fact that we can have our dienes and dienophiles have different stereochemistry. And the main thing to note is that we need to have our dienes, or we want to have our dienes, we want to think about them being very stereospecific. So if we're thinking about our syn addition, we're saying that both components kind of form on the same side of the molecule. And we have a few examples to kind of illustrate how our dienes and dienophiles can react, right? So let's take some dienes and dienophiles. So let's look at a few examples, right? And let's take dienes and dienophiles. Let's pick some that are consistent. So let's start off with just a basic diene. Right, so we're starting off with a basic diene, and we're going to choose our dienophiles to be, we'll start off with cis versus trans dienophiles. So if we have in this case, you can see that we have, if we look at some of the dienophiles given, right, we have a trans dienophile species here and a cis dienophile species here. Right, so this is trans versus cis, and they have the same, so they're isomers because they have the same chemical formula, right? But the stereochemistry is different, so they're stereoisomers. And if we were to combine our diene with our dienophile, so if we have C double bond O, our ester species, right? So this would be our, actually I want to draw that last carbon in the opposite direction just to make it a little bit prettier. So this would be our cis ester. And if we want our trans ester, then we'd have our carbonyls and our ester functional groups in opposite directions. And what we're saying here is that when we combine our cis dienophile, we'll get a cis product, right? So we'll get a ring. And then on our ring, our functional group should be on the same side of the molecule for our cis product. So we'll get a carbon with a double bond to oxygen and a methyl. Right? So for our cis dienophile, we'll get a cis product. And you can imagine that we can either have this as the dashed or wedged species, right? I could technically draw this. I could redraw this as just a straight line and say that it's racemic. And say that it's, oh, where's my writing going? Racemic. Right? That's another way that I can do it. But if you do include the stereochemistry, you want to indicate that both products are formed, right? So that's our cis dienophile, and we're thinking about syn addition, meaning that we have both components occurring. We want both of our activity sites to occur on the same side. So what about our trans reaction? So for our trans reaction, if we want to take our trans dienophile and react it with our diene, then what we'll get is a product where the substituents, right, on our new ring now are trans to one another, right? So now we have one ester functional group that will be wedged and the other that will be dashed, right? So that would be the difference between our cis and trans products based on having a cis or trans dienophile. So that's one example. What if we have substituents where the stereochemistry is the same? So let's take the same dienophile, or same let's pick a dienophile that's a little different. So now we're going to take a dienophile where we actually have 2 pi bonds present in our molecule. So let's pick a dienophile that's a little bit different. And for this dienophile, we want to use a triple bond. So we'll take a triple bond, and as a part of our triple bond, we'll use an ester again, ester functional group. Right, so now this is a different dienophile. And let's also pick a different diene. So now let's add substituents to our diene. We'll just add methyls to each carbon. That's a part of our double bond. And if we were to think about the products present from this molecule, if we have our diene where our substituents on our diene are in the same location, right, on the same location, then we'll consider our product to be symmetrical as well, right? So we'll have symmetrical methyls present on our molecule, where if we were to think about our electron pushing here, right, we'll have an electron, or for our electron pushing mechanism, we'll have electrons pushed there, there, and there, forming our 6-membered ring. We've only used one set of pi electrons, or one of the bonds in our triple bond, to generate our ring. So that must mean that our ring must contain another double bond over here. And then a part of this, we should also have our ester functional group on each side, right? So that would be the product if we have if we look at our diene with our substituents on the same side. But what if our substituents are on opposite sides? So let's change our reaction. And now let's put our second methyl on the inside, right? So we have a methyl on the outside, a methyl on the inside. We'll talk more about outside, inside on our diene in a minute, right? But now we've changed the stereochemistry of our diene. We're reacting it with the same dienophile. And now with this reaction, we'll see that the stereochemistry for our methyl groups will be inverted. So we don't have a change in the stereochemistry on our dienophile, but this, because we're saying that we're adding it to a cyclical ring, that'll be planar, right? And because we've chosen to use a triple bond here, right, that means that the bond here, the bonds at those ester sites are restrained. So we'll have a double bond present because of the original triple bond that we had present. And now you'll see that because we've changed our location of our substituents on our diene, you'll see that now the stereochemistry for our cyclical, for substituents on our cyclical ring is now different.